So here's the question of collision and rotational motion. What happens is that a particle of small mass m with initial velocity v0 comes and strikes this solid sphere of radius r and mass m and sticks to it. What we need to find out now is the linear speed of the combined system after collision, the angular speed, and the value of h for which the solid sphere along with the particle starts doing pure rolling after collision on the plane. So for solving this question, let us solve the first part first. Let us look at this system in the horizontal direction. The net external force acting on the system in the horizontal direction for the small duration of collision is 0, due to which the momentum of the system remains conserved in the horizontal direction. The frictional forces and all other forces which may act in the horizontal direction are too negligible to produce some effect in the small time duration of collision. So we can directly apply momentum conservation on this system for before and after the collision. So we get mv0 is equal to m plus m into v dash, that is vcm, after the particle collides and sticks. So the linear velocity can directly found out to be mv0 upon m plus m by applying linear momentum conservation on the system for the case of before and after the collision. So we get the answer for mv0 upon m plus m is our linear velocity. Now we need to find out the angular velocity of the system after the particle has collided with it. So for that, we can use angular momentum conservation about the center of mass. Because there is no external torque acting on the system in the horizontal direction about the center of mass, therefore we can apply, it's not about horizontal direction now, there is no external torque acting on the system about the center of mass, therefore we can apply angular momentum conservation about the center of mass on this system. Therefore initial angular momentum can be written to be equal to the final angular momentum. The initial angular momentum can be written as m v0 into r perpendicular. R perpendicular is the perpendicular distance from the line of momentum from the point about which you need to find out the angular momentum, that is equal to h minus r. Therefore m v0 into h minus r is equal to final angular momentum of the system when it has this mass stuck to it. Now we need to write down the final angular momentum of the system. Now we know a formula for the angular momentum of a system, that is equal to ICM into omega vector. Now let the angular velocity developed in the object after collision be omega. So we can write the angular momentum of the system to be equal to its moment of inertia into omega. We have assumed omega in the clockwise direction because this produces an angular momentum in the inside direction, which is the same as angular momentum produced in this direction, that is inside. Therefore now we write down the moment of inertia. Moment of inertia of a solid sphere about its center of mass is 2 by, about an axis passing through its center of mass is 2 by 5 mr square. Now we need, you must not forget an additional term which comes here, which is mr square, due to the particle being stuck to it, and therefore the additional moment of inertia of this particle about the center of mass comes out to be mr square. So we get this equation and we solve it to get the value of omega as mv0 into h minus r upon 2 by 5 m plus m into omega r square into r square. Sorry. Therefore the final value of the angular velocity of the system about its center of mass comes out to be mv0 into h minus r upon 2 by 5 m plus m r square. Now the question is, for the third part, the question is for what value of h does the object starts doing pure rolling after collision. So for pure rolling, the velocity of center of mass that is developed should be equal to omega r. If initially this condition is satisfied, then the object starts doing pure rolling. So we just equate it, mv0 upon m plus m is equal to mv0 into h minus r upon 2 by 5 m plus m into r. 1 r square r, this r gets cancelled with the square. So on solving this we get the value of h to be equal to 7 by 5m plus 2m upon m plus m into r. Now while solving this question, we made one important assumption which you should keep in mind, that when this particle gets attached to the sphere, the center of mass of the whole system changes. But we assume the center of mass to be still at the center. So an important assumption which I forgot to mention was that this mass is smaller, very small as compared to the mass of the sphere, due to which the center of mass can be assumed to be almost at the same point. But we cannot neglect the moment of inertia which we have already added here. So the height above the ground at which this particle should have been initially is equal to 7 by 5m plus 2m upon m plus m into r. Now this m being very smaller than capital M can be neglected as compared to capital M to give the result h is equal to 7 by 5 times r. So final answer for the height h comes out to be 7 by 5 r. The velocity of center of mass comes out to be linear velocity to be m v naught upon m plus m, and the angular velocity comes out to be m v naught into h minus r upon 2 by 5 m plus m r square.